Welcome. You are about to view a recorded talk of the Mathematical Consciousness Science online seminar series. This seminar series aims to explore the role of mathematics in the scientific study of consciousness and hopes to connect researchers who have an interest in this topic. While every session of the seminar consists of a talk and discussions, the latter are not recorded and the following will only contain the talk. We hope you will enjoy it. For further information, please visit our website, seminar.math-consciousness.org.
Thank you all for coming. And thanks very much to the organizers for inviting me to speak. I'm really grateful to have the opportunity to share my work with this audience, especially because, as Johannes just said, the motivation and the theme of this seminar very much aligns with my own research interests. As he said, one of my main research projects is on how conscious experiences are structured and how to formally model that structure. And part of why I'm interested in this is because I think that investigating the structure of experience provides a way for us to make progress on consciousness research without needing to take a stance on the mind-body problem or the nature of perception or even the neural correlates of consciousness. And more generally, if you look at any scientific field, an essential component of scientific knowledge is knowledge of how the target of inquiry is structured. And the best tools that we have for understanding and describing structure are mathematical tools. So in my view, the application of mathematical tools to consciousness research is a really promising way of advancing the study of consciousness. What I'm going to present today is one part of this larger project. The central question that I'm going to focus on is, how do we model the mental qualities of conscious experiences? Qualities like those involved in seeing red or feeling pain or smelling cinnamon. So here's what I'm going to aim to do. I'm going to first argue that the standard framework for modeling mental qualities is inadequate. And then I'm going to develop a new framework that is more powerful and flexible. I'll explain how philosophical questions about the structure of experience correspond to mathematical questions about the formal structure of this framework. And then at the end, I'll show how the framework has applications to some other theoretical issues concerning consciousness. This talk is going to be based off of a forthcoming paper. Just to warn you, I'm going to move fairly quickly through the content of the talk, and I'm only going to have enough time to cover the basic philosophical and mathematical ideas. And I've also left out a good deal of the materials. So if you want to look at the arguments or the formal definitions in more detail, if you want to pin me down on something, then it's probably best to just look at the paper itself. You can just Google it and it's easily findable. And that can provide a way for you to look at things longer than what I just have on the slide. So let me start by saying a few things about what I mean by the standard framework. So the standard framework, what I'll call the standard framework, models mental qualities via points in geometrical spaces, where distances between points correspond to degrees of phenomenal similarity. So these are sometimes called quality space models. And the most familiar example of a quality space model is the three-dimensional model of color experience, where hue, saturation, and brightness are the dimensions. You see an illustration of that model here, and you can see how there's this nice systematic representation of all of the similarity relations between different color experiences that is captured by this model. Now, color is the most well-known and prominent example, but in principle, we could also develop quality space models for the qualities involved in auditory experience or olfactory experience or just about any other domain of experience. Because for any domain, there's going to be similarity structure. And as long as there's similarity structure, we'll be able to model that similarity structure using a metric, and we'll be able to develop a quality space model for that domain. So if one of our goals is to map out the structures of conscious experiences, then a significant part of that project will be to develop quality space models for different domains of experiences. Now, one terminological note, I'm going to frame everything I say in this talk in terms of mental qualities, but I'm basically going to treat this term as synonymous with terms like phenomenal qualities or qualia. Maybe those are more familiar with to some of you, but I'm just going to use the terminology of mental qualities. So here's the structure of the talk. First, I'll say a few more things about the standard framework. I'm not going to say too much there. I'm going to quickly move to the new framework that I want to develop, which I'll call the regional framework. And at the end, I'll talk about some applications and implications of the regional framework. As I said, I won't be able to cover everything. I'm going to focus on presenting enough of the philosophical background and mathematical ideas to make the core content understandable. But if you want the full arguments or the reasoning that leads to the formalisms, then it's easiest to look in the paper itself. So let me start with a few basic distinctions that I'll just quickly go through. First, I'll distinguish mental qualities of conscious experiences from perceptible qualities of external objects. So mental qualities are things like color experiences, whereas perceptible qualities are things like colors. When I talk about perceptible qualities, these should be distinguished from physical stimuli. Perceptible qualities are things like colors, whereas physical stimuli are things like wavelengths of light. You can think of any given perceptible quality as realizable by different physical stimuli. The reason this distinction is important is because oftentimes in both philosophy and cognitive science, you'll see people say that there's an isomorphism between mental quality spaces and perceptible quality spaces, that mental qualities have the same structure as perceptible qualities. And that claim is plausible only because we're talking about perceptible qualities rather than physical stimuli. Perceptible qualities understood at a coarser level of abstraction. Now, I'm also going to distinguish models from targets. So a model you can think of as a formal representation, whereas the target is what's being represented. I'll later be talking about modeling mental qualities using regions in geometrical spaces rather than points. There, the regions are features of the model. The mental qualities represented by the regions are the targets of the model. And then last, I want to distinguish between what I call frameworks versus models. So you can think of a model as a formal representation of a particular domain of mental qualities, whereas a framework is a general schema for developing models. In order to construct a model for any particular domain of mental qualities, we have to empirically investigate that domain. But in order to develop an adequate framework, what we have to do is specify what kind of formal structure is required for modeling any arbitrary domain of mental qualities, regardless of how any particular model is structured. So what I'm going to do today is argue that in order to adequately model mental qualities, we have to make basic changes to the whole quality space model framework rather than just patches or tweaks to particular models. Let me say a bit more about the standard framework to characterize it more precisely. So if we think about the formal structure of any model within the standard framework, then there's going to be two formal elements. First, a set of points, and second, a distance metric. And in order for the model to be representationally adequate, there has to be a few criteria that are satisfied. First, there should be one-to-one correspondence between points in the model and qualities in the target domain. Second, we want distances between points to inversely correspond to degrees of phenomenal similarity. You see that in the three-dimensional color solid that we saw earlier. And then third, we want phenomenal identity to entail distance zero. We want two qualities to be the same just in case their distance is zero. So something I'm going to argue in a moment is that none of these criteria can be satisfied for any standard model. And the basic reason for that is because of what I'll call phenomenal precision. So to get a grip on precision, think about the phenomenal contrast between, for example, your foveal color experience of something as scarlet versus your peripheral color experience of something as red. Your foveal color experience is more precise than your peripheral color experience. It's not just that your peripheral color experience represents a different specific shade of color. Instead, it seems to be less specific in which shade of color is being represented. if we think about the perceptual knowledge that you can acquire on the basis of your experience, then you'll be able to acquire more specific, more fine-grained knowledge on the basis of the precise color experience than on the basis of the imprecise color experience. So this phenomenal contrast between foveal and peripheral color experience, I think, is the clearest example of a difference in precision, but we can think about other examples as well. So for example, think about the difference in color experience between your experience of an object from close up versus far away, or the phenomenal contrast between your visual experience when you have glasses on versus glasses off, or your tactile experience when you're touching something, say, with your fingertips versus with your back. In each of these cases, the first experience is more precise than the second experience. Now, there's questions we could ask about the nature of precision. I'm going to be largely neutral on these questions, mostly because I think that it's pretty straightforward to answer these questions, depending on which theory of perception you favor. So if you're a representationalist, it's very natural to think that precision is a matter of the specificity of the representational content of an experience. If you're a naive realist, it's natural to think of precision as a matter of the determinability of the external properties that we're perceptually aware of. If you're a quality theorist, then it's natural to think of precision as a basic structural feature of experience, kind of akin to the resolution of an image. Now, the framework that I'm going to develop is compatible with all these theories. And that's a virtue of the framework, because what that means is that no matter what kind of philosophical theory of consciousness you endorse, you can employ the framework that I'll be developing. It provides a common basis, a common language for theorists of different stripes. So I'm not really going to be concerned with questions about the nature of precision. Instead, what I want to focus on are questions about the structure of precision, and more specifically with the question, how can our quality space models capture the precision structure of mental qualities? Now, in a longer version of this talk, or a version of this talk that would be pitched more to just philosophers, I would go on a slight tangent now and talk about the difference between precision and indeterminacy. Basically, precision is not the same as what philosophers call determinacy or determinability, the relationship between determinates and determinables. I'm not going to go into this just for purposes of time. I'm going to try to focus more on some of the mathematical ideas and skip over some of the distinctively philosophical stuff. But if you're interested in this distinction, then feel free to ask in Q&A, or I have the full argument in the paper. Now, it's pretty easy and intuitive to see why there's a problem with a standard framework once we recognize the existence of precision. And the core problem is that the standard framework models mental qualities via points in geometrical spaces, but imprecise experiences seem to correspond to regions rather than points. So the standard framework is structurally inadequate. Now, one thing that a lot of people think at this point is, well, couldn't we just add an extra dimension to our quality space models that represents degree of precision? So for example, instead of a three-dimensional color space, couldn't we just augment it and turn it into a four-dimensional color space that has hue, saturation, brightness, and precision as dimensions? This is one way to go, but it's not a good option for two reasons. One is that this approach makes some substantive assumptions about the structure of precision. For example, it rules out the possibility that a mental quality can vary with respect to precision, that a mental quality's hue can vary in precision independently from its brightness, that precision with respect to hue, for example, can vary independently from precision with respect to brightness. That's a view that some might have. You might think that precision has more structure than what can be captured by just adding an extra dimension. And if we're trying to develop a framework for modeling mental qualities, then presumably it should be neutral on these different views. It should be able to accommodate all sorts of different views about the space and structure of mental qualities. That's something that the framework that I develop is going to be able to do. A second problem is that adding an extra dimension would make it hard to account for similarity with respect to precision across different domains of mental qualities. And the reason is that we're modeling phenomenal similarity using distances between points in geometrical spaces, but there are no distances when we're looking at different spaces. So there's a puzzle of how we would capture similarity with respect to precision when we're looking at, say, color experience versus auditory experience. And I'll explain later on how the new framework that I develop can capture similarity with respect to precision, even when we're looking at different domains of mental qualities. Now, there's more that I could say to solidify the argument that the standard framework is inadequate, but what I've said conveys the basic problem. And I want to spend most of this talk on the new framework that I developed, because I think that's where the most interesting philosophical and mathematical action lies. So I'll just move forward. Okay, so what I'm going to do now is develop the regional framework. The basic idea behind the regional framework is we're going to model mental qualities via regions or sets of points rather than individual points. So when we were looking at the structure of the standard framework, I listed a few different criteria for representational adequacy. We again have the same criteria for the regional framework with one new one. The new one being the sizes of regions should correspond to degrees of precision. So the basic idea behind the regional framework is that the bigger the size of the region that represents a mental quality, the greater the degree of imprecision of that mental quality. So bigger regions mean more imprecise mental qualities. And then again, we want one-to-one correspondence between what I'm going to call permissible regions, which I'll explain in a moment, and qualities. We want distance to vary with phenomenal similarity, and we want phenomenal identity to entail distance zero again. Now, in the standard framework, it's pretty simple to specify the formal structure of a model. We just need two elements, a set of points and a distance metric. In the regional framework, things are more complicated. We need more formal elements. We again need a set of points and a distance metric, but we're also going to need a measure. This is a function that takes as input a region and that outputs a size value. We're going to need a set of regions, which I'll talk about in a moment. And then we're also going to need some distance metrics on regions that take as input regions of arbitrary shape and arbitrary size, and that output intuitive measures of distance. So it's going to be a substantial task to get all of this together to find the right metrics and the right measure and so forth. And I'll walk you through some of these steps in the following slides. Okay, so the elements that I'm going to focus on are going to be highlighted at the bottom. And I'm just going to very quickly say a few things about the first three elements. So the set S of points and the point distance metric D, these determine the structure of the space. So they determine whether the relevant space is, for example, continuous or discrete, the dimensionality of the space, the boundaries of the space, and so forth. I'm going to largely skip discussion of these elements, mostly because the relevant questions that arise when we think about these elements also arise when we're thinking about the standard framework. So if you look at prior literature in philosophy and cognitive science on mental qualities and quality spaces, then there's a whole lot of discussion of these sorts of issues. There's, for example, a whole lot of discussion on how we should use empirical methods to construct quality spaces, and they largely generalize to the regional framework as well. So I'm not really going to focus on these elements. And there's also, the third element is the measure, which I'll call mu, which is a function that takes as input a region and outputs its size. And I'm going to largely skip discussion of this element as well. And that's because most of the questions here are largely technical rather than philosophical. There's not a nice intersection between the philosophy and the math like we'll see in a moment. Now, I guess I'll mention one interesting question about the measure is if we're thinking of the relevant spaces as continuous, you might ask, how do we develop a measure for that works in continuous spaces? Because If the spaces were discrete, then it's pretty easy to measure region size. We would just take the size of a region to be the number of elements in that region. So we would take size to just be cardinality. But in a continuous space, every region is going to have an infinite number of points. So the cardinality of basically every region is going to be the same. I think there's a nice way of getting around this that's well developed in mathematics. I talk a little bit about the Lebesgue measure in the paper, but I'm going to skip this because that doesn't really intersect with the philosophical issues that I want to focus on. So what I want to spend most of the time on is the last two elements, the set R of regions and the region distance metrics, which I'll call QUAL and PREC. So one thing you might be thinking is, why do we even need a set of regions? Because couldn't we simply take regions to be subsets of the set of points? We already have the set of points that tells us the structure of the space. And it's natural to think that, well, any subset of that set of points is going to be a region. And that's correct. A region is just a set of points. And we can think of the set of regions as any subset of the set S of points. You can think of the set of regions as the power set of S. But we should distinguish regions from what I'll call permissible regions, where a permissible region is a region that represents a mental quality. And that's what the set of regions is supposed to be. It's the set of permissible regions. And the reason we want this distinction is because most theorists are going to think that the set R of regions is not the same as just the power set of S. Most people are going to think that there are some regions that are not permissible regions that don't represent genuine mental qualities. For example, think about the three-dimensional color space that we saw before. Imagine a region that is disconnected, that just contains a few points on opposite ends of the color space. For example, you might imagine a region that represents a mental quality that itself represents either scarlet or aquamarine, but nothing in between. And you might wonder, is that really a possible mental quality? Could you have an experience that represents something as either scarlet or aquamarine, but no shades of color in between? It's not obvious that that is a genuine mental quality. It's not obvious that we could conceive of that. So we might want restrictions on the set of regions. Now, there's a question then, how do we actually define the set of regions? How do we separate the any region whatsoever from permissible regions? And one cool thing about the framework is that different formal principles for limiting the set of regions correspond to different philosophical theories about the space and structure of mental qualities. So here's what I mean. Here's a diagram with 4 different sample regions. You can just imagine this to be a toy example of a quality space, and these are 4 different regions in that space. Now, if you're extremely permissive about mental qualities, then you might accept a principle like universality. All regions are permissible. So this kind of theorist would think that regions A, B, C, and D all represent genuine mental qualities, that it is possible to have an experience that represents either scarlet or aquamarine, but nothing in between. But I think a lot of people will think that, no, that's too liberal. We ought to be more restrictive about the space of possible mental qualities. So one thing you might want to do is disallow disconnected regions. You might adopt a principle like connectivity. All permissible regions are connected. This would permit regions A, B, and C, but exclude D. Or you might want to be more conservative and think that only convex regions are ones that represent genuine mental qualities. Or you might be ultra conservative and accept something like uniformity. All permissible regions are balls, where a ball is the set of points that are within some distance from some center. So I'm not going to take a stance on which of these principles is correct. I just want to point out that we're now able to actually ask these questions, and these are philosophically interesting questions. It's not very obvious which of these views is correct. They paint substantially different pictures of the space and structure of mental qualities. One nice thing also is that all of these principles that I've listed here are able to be well defined formally. So if you look at the paper itself, then I have formal definitions for all these different principles. And what that does is it allows us to theorize about mental qualities at a greater degree of systematicity and rigor than we were able to before. In fact, think about how hard it would be to even formulate these kinds of questions in the first place without the use of this framework. So I think that already this provides a glimpse of how the regional framework enables us to address philosophical issues about the space and structure of mental qualities with greater precision, and to raise some new questions that we previously didn't really have the conceptual tools to even think about or talk about. Okay, so as I said, I don't want to take a stance on which of these principles is correct. Instead, I just want to show how the regional framework provides a nice tool for theorizing about mental qualities. I'll move on now to the last elements of the regional framework, which are the distance metrics. And just to situate things, what we're looking for is a distance metric that takes as input two regions of arbitrary shape and arbitrary size that might overlap with each other. Maybe one contains the other, and that outputs distance values that systematically correspond to degrees of similarity, and that satisfy the constraints on a phenomenal similarity metric that we saw earlier. So that's a substantial task, to find a metric that actually satisfies these constraints. And to show why that's the case, let's walk through a few candidates for metrics on regions. So here's the first candidate. It's the least distance metric. The least distance between region A and region B is the distance between the closest points between A and B. So if you look at metrics that are actually used on regions, the least distance metric is probably the most popular metric. It's arguably the standard metric for measuring distances between regions or between sets. But this isn't a good metric for our purposes. And one way to see that is to consider the following diagram. So imagine that we have a space and there's regions A and B, and suppose that A and B just slightly overlap with each other. So for example, maybe A is a region that represents an imprecise red experience, and B is a region that represents an imprecise purple experience. And maybe there are some shades of red that are also shades of purple, but just a couple. Now, if we apply the least distance metric, then we're going to get the result that the least distance from A to B is 0, because there are some points that are shared between A and B. So the distance between the closest points is 0. But distance 0 represents phenomenal identity, and A and B represent non-identical qualities, because remember, we want two regions to be distinct just in case the mental qualities represented by those regions are distinct. So the least distance metric doesn't work as a metric for measuring phenomenal similarity within the regional framework. Here's a much more promising metric, the average distance metric. So one thing that you might think is wrong with the least distance metric is it's not sensitive to all of the points between the regions. We want a metric that looks at all of the points in A and all of the points in B, and is sensitive to all of those points. And that is a feature of the average distance metric. So here's how the average distance metric works. The average distance between A and B is the average distance between the points of A and the points of B. Or more specifically, to find the average distance between A and B, what we're going to do is we're going to take a point of A, we're going to find its distance to every point of B, and we're going to average those distances. And then we're going to repeat the procedure for every other point of A, and then take an average of those averages. So the average distance metric is pretty good. It works well in a lot of cases, but it also doesn't work as a way of measuring phenomenal similarity. And that's most obvious when we consider the average distance from any region to itself. So suppose that we take the average distance from A to A. Well, as long as A contains more than one point, the average distance is going to be greater than 0. But obviously, A is phenomenally identical to itself. The mental quality represented by A is phenomenally identical to itself. And phenomenal identity is supposed to correspond to distance 0. So the average distance metric is giving us the absurd result that any mental quality is not maximally similar to itself. So that's the wrong result as well. Now, this means that the average distance metric fails, but I think it's still on the right track. And the metric that I'm going to propose is based off of the average distance metric. And in particular, it's based off of the following two observations. First, the average distance metric actually works well, except in cases involving overlapping regions. As long as two regions are disjoint from each other, then the average distance between those regions is going to correspond in very intuitive ways to the degrees of phenomenal similarity between the mental qualities represented by those regions. That's the first observation. Second observation, any case that involves overlapping regions can be treated as a pair of cases that involves disjoint regions. And here's what I mean by that. Consider the following situation. So suppose that we have regions A and B, and they overlap with each other. They're both rectangular regions this time. So A is this long rectangle to the left, and B is this long rectangle to the right. And then there's also a subset of B that is not in A, which I'll call B complement A. And there's a subset of A that is not in B, which I'll call A complement B. And the way that the metric that I'm proposing works is to find the distance between A and B. What we're going to do is we're going to break this case into two cases and apply the average distance metric twice. More specifically, what we're going to do is first, we're going to find the average distance from A to B complement A. So these are going to be disjoint regions. And then we're going to find the average distance from B to A complement B. These again will be disjoint. And then we're just going to take a weighted average of those results with the weighting in proportion to the relative sizes of A and B. So again, what this is doing is that it's in any case that involves overlapping regions, we're just going to break things down into two cases by looking at the relative complements, by looking at the subset of each region that is not in the other. And then we're just going to apply the average distance metric twice and take a weighted average. When we formalize this, we get the following equation. Here's the same equation that is in diagram form. So this metric is what I think is the right metric. This is the metric that I'll call the QUAL metric, short for the qualitative similarity metric. And I'll just read off the formal equation. So according to this metric, the qualitative similarity between A and B, meaning the degree of similarity between the mental qualities represented by a region A and a region B, is the following. The average distance from A to B complement A times the size of B complement A, plus the average distance from B to A complement B times the size of A complement B. And then we're going to divide that by the size of the union of A and B. Now, I know that this is this will take a moment to wrap your head around, but I think that when you get a grasp of how this works, it's a pretty intuitive procedure. And one way to see why this is a plausible metric is to see how the metric behaves in the different kinds of situations that can occur between two sets. So, for example, suppose that A and B are identical to each other. So they're regions that represent the same mental quality. Then we're going to get the result that QUAL of A and B is equal to 0. So identical mental qualities correspond to zero distance, correspond to maximal phenomenal similarity. Second, suppose that A and B are disjoint from each other, then the QUAL metric just collapses into the average distance metric. And As I noted earlier, the average distance metric works well in disjoint cases. We only get the weird, wonky results when there's overlap, where that's most obvious when we consider the average distance from a region to itself. So that's good too. Now, if A and B overlap with each other, then it's guaranteed that QUAL of A and B is going to be greater than 0. So what this means is that in cases of partial overlap, there's not going to be maximal phenomenal similarity. And then same thing in cases of containment. In cases of containment, there's not going to be maximal phenomenal similarity according to the metric. And on top of that, in either cases of overlap or in cases of a containment, if other things being equal, we decrease the amount of overlap between A and B, or we increase the difference in relative size between A and B, the distance between A and B is going to be greater. And that is what we intuitively want the metric to behave like, given that it's measuring phenomenal similarity. So this is all to say that there are principled reasons for thinking that the QUAL metric is the right metric. It's the metric for measuring phenomenal similarity that we were looking for. And that's a pretty substantial result because the least distance metric didn't work, the average distance metric didn't work, and other standard metrics on regions don't work either. For example, the Hausdorff metric, that's another popular metric for measuring distances between regions. That doesn't work either. So, okay, so that's great. We started with this challenge. How do we measure degrees of phenomenal similarity between mental qualities using the regional framework when we're representing mental qualities using regions rather than points? It wasn't obvious that that challenge could be surmounted, but now we have this nice, relatively simple formalism for addressing that challenge. Still, in spite of these virtues, I think that there's still a problem, a limitation with the QUAL metric. And one way to see that is to consider the following situation. So suppose that we have these three regions, A, B, and C. Suppose that A represents a relatively precise blue quality, and B represents a relatively precise green quality, and that C represents a relatively imprecise green quality. Now, if we apply the QUAL metric, then we're going to get the following result. QUAL of A and B is the same as QUAL of A and C. And one way to see that is to just remember, when we're working with disjoint regions, the QUAL metric works the same way as the average distance metric. And the average distance from A to B is the same as the average distance from A to C. You can see that spatially in this diagram. But here's the thing. A is more similar to B than to C because A and B are similar with respect to precision. I mean, just think about the mental qualities that are represented by these regions. Think about a precise blue experience that you might have in full field visual experience and a precise green experience versus an imprecise green experience that you might have in peripheral visual experience. These are different in their qualitative character, the blue and the green ones, but the precise blue experience seems similar to the precise green experience with respect to precision. So there's an aspect of phenomenal similarity that the QUAL metric doesn't capture. Now, here's my response. I think that this is actually a feature rather than a flaw of the metric that I've developed. And the reason for that is that we should distinguish between qualitative similarity and precision similarity. And it's pretty intuitive to see the difference between these two kinds of similarity. I mean, think about the kind of similarity we have in mind when we say that red experience is more similar to orange experience than to green experience, versus the kind of similarity that we have in mind when we say that a precise blue experience is more similar to a precise green experience than to an imprecise green experience. These intuitively seem to be just different dimensions of phenomenal similarity. And I think it's a virtue if our metrics, if our models of mental qualities differentiate between these two different dimensions. So I think the lesson here is that in addition to a metric measuring qualitative similarity, the QUAL metric, we need another metric that measures precision similarity, which I'll call the PREC metric. And luckily, the PREC metric is pretty easy to define because remember, in the regional framework, degrees of precision are represented by region sizes. So what that means is that to find the degree of precision similarity between two mental qualities, we should look at the how different in size the regions representing those qualities are. And there's basically two options that we have here. One is to take the difference in size between regions, and the other is to take the ratio. These are two different ways of measuring differences in region size. For reasons I won't go into here, I think the ratio measure is better. I'm happy to talk about that in Q&A if people are interested. But here's how we would go about constructing the PREC metric on the ratio approach. So let's define the minimum of A and B to be the size of the smaller region between A and B, and the maximum of A and B to be the size of the larger region. Then the PREC metric just takes the degree of precision similarity between A and B to be the ratio of the minimum over the maximum. So it's very simple. It's very easy to grasp. And one nice thing here is that this metric doesn't encroach on qualitative similarity. It doesn't overlap with respect to the aspects of phenomenal similarity that it's measuring. So given that, I think that the QUAL metric and the PREC metric are carving things at their joints. It's providing two different ways of measuring phenomenal similarity that track two different dimensions of phenomenal similarity. Now, one thing we could do is ask, well, is there an overall phenomenal similarity metric that gives us a single similarity value? I guess speaking for myself, I'm skeptical that there's a fact of the matter about how to weigh qualitative similarity against precision similarity. If you did think that there is a fact of the matter, though, then we could always look for a new metric that's a bit more complex, or just take the conjunction of QUAL and PREC, maybe with some weighting to weigh the outputs against one another. Okay, so to recap, what I've been doing during this section is explaining the formal structure of the regional framework. The core idea, again, is to represent mental qualities via regions rather than points. Imprecise qualities correspond to bigger regions. Degree of precision is measured by size of region. And I've talked about, I mentioned before the different formal constraints on a regional model. I've given some arguments for why these formal constraints can be satisfied. What I've said in this talk doesn't go through these systematically, but you can kind of see why the regional framework alongside the metrics that I've developed enable us to satisfy these formal constraints. And then I've briefly gone through some of the elements of the regional framework. I didn't say much about the set of points, the point distance metric, or the measure, but I explained how different constraints on the set of permissible regions correspond to different philosophical theories about the space and structure of mental qualities. And I've also gone through some of the reasoning in our search for the region distance metrics. And I've argued that when we think about the region distance metrics, we can differentiate between two different dimensions of phenomenal similarity. Okay, so what I want to do in the last part of this talk is just talk about some applications of the regional framework. And I'll talk about two applications and then one implication. So the first application concerns discriminatory grain. So here's what I mean by discriminatory grain. Here's a scenario. Suppose that Kiki and Baba are two different subjects. And suppose they're like in a psychophysics experiment and they're both looking at color chips. They're presented with 50 color chips. Suppose that Kiki's color discriminatory capacities are pretty good. Kiki can make 36 discriminations over those 50 color chips, whereas Baba's color vision is not so good. Baba can only make 9 discriminations over those same 50 color chips. Then Kiki's discriminatory capacities are finer than Baba's. This is just explaining what I mean by discriminatory grain. The discriminatory grain of Kiki's color capacities is finer than the discriminatory grain of Baba's. Okay, so here's a hypothesis that is very natural. Kiki's color experiences are also more precise than Baba's color experiences. In other words, this hypothesis is saying that there's a connection between a certain phenomenal property, namely precision, and a certain functional property, namely capacity to make perceptual discriminations. I think almost everyone will find this hypothesis very plausible. It's very natural to think that the functional role of precision is discriminatory graying. If you just think about your own experiences, think about, for example, how your experience of scarlet and crimson and aquamarine and so forth, these precise experiences enable more fine-grained discriminations than your imprecise experiences of red or green or purple. So this is a very natural hypothesis. Now, this is all still just setting things up at a qualitative level. There's one more thing I need to do to set things up to develop the formal analysis that I'll talk about in a moment, and that's to distinguish between what I'll call strong discriminability and weak discriminability. So let's say that two stimuli are strongly discriminable just in case the experiences representing those stimuli correspond to disjoint regions. And that two stimuli are weakly discriminable just in case the associated regions are not disjoint, just in case they overlap, just in case they partially overlap. So I think that this distinction between strong and weak discriminability is important for understanding the nature of perceptual discrimination. One way to give you a grip on this distinction is let's say that alpha and beta are two different stimuli. They're two different color chips, for example. Now, if alpha and beta are strongly discriminable, then the subject that is experiencing alpha and beta can be sure, if they take their experience at face value, that alpha is distinct from beta, because their experience of alpha, the region representing their experience of alpha is disjoint from the region representing their experience of beta. So there's no overlap between the content of the experience representing alpha and the content of the experience representing beta. Now, if alpha and beta are only weakly discriminable, then the subject can't be sure solely on the basis of their experience whether alpha and beta are distinct. But nevertheless, weak discriminability still entails that the way that alpha looks is distinct from the way that beta looks, since weak discriminability involves distinct regions, and distinct regions represent distinct qualities. Okay, so just to recap, what I've done is first I presented a scenario involving Kiki and Baba where they're making color discriminations in order to define what I mean by discriminatory graying. Then I presented a hypothesis connecting degree of precision with discriminatory graying. And then I presented this distinction between strong discriminability and weak discriminability. And what we can do is we can take all these things and put them together to develop a formal analysis of the degree of discriminatory graying of a perceptual capacity. And I'm just going to read the formal analysis and then I'll explain it in a moment. So the formal analysis is that the discriminatory graying of a perceptual capacity, like a subject's color vision, is measured by a maximization of strong discriminations conditional on a minimization, meaning zero, of weak discriminations for that perceptual capacity. Or equivalently, the discriminatory graying of a perceptual capacity is the maximally large set of mutually disjoint regions for the mental qualities associated with that capacity. So here's an intuitive way of thinking about this, returning to the Kiki and Baba case. Suppose that we look at Kiki's color discriminatory capacities, and we look at all of the color experiences that Kiki can have. And then we look at all of the regions that represent those color experiences. And then we take those regions and we try to fill up the corresponding space that those regions belong to as tightly as possible without allowing any of those regions to overlap. Now, because Kiki has a bunch of precise color experiences, we're going to be able to fill up that space with a lot of those regions. You can see that here. By contrast, if we were to take Baba's color experiences and the associated regions and try to fill up the corresponding space, then we wouldn't be able to do that as much. We wouldn't be able to do that while conditionalizing that none of the regions can overlap with each other. So then the formal analysis is saying that to measure the discriminatory graying of a perceptual capacity, we just look at how many of these regions can fill up the corresponding space, and that's our measure. And I think that's a pretty intuitive measure. I think it'll deliver the right verdicts across different cases, like this Kiki and Bava case. And I think that's pretty cool. We start off with this purely qualitative idea that there's this connection between perceptual discrimination and phenomenal precision. And using the regional framework alongside some very plausible hypotheses, we can get this precise measure of the degree of discriminatory grain of any perceptual capacity. Okay, so that's the first application. Second application is going to be to what's sometimes called the phenomenal SORITES. So a phenomenal SORITES is a case where a subject is able to experience stimuli alpha, beta, and gamma. Again, imagine that they're color chips. And the subject cannot discriminate alpha from beta or beta from gamma, but can discriminate alpha from gamma. So I tried to actually set up a phenomenal SORITES here. Maybe it'll work on you, maybe it won't, but these are all different shades of gray. So here's a diagnosis of the situations in which phenomenal SORITES cases can occur. A phenomenal SORITES can occur just in case, so alpha, beta, and gamma are three different stimuli. Let's suppose that A, B, and C are the regions representing the mental qualities for the subject's experiences of those stimuli. So the subject sees color chip A, they have an experience of color chip A, and that experience is represented by region A, and then so on for beta and B and gamma and C. So the diagnosis here is that a phenomenal SORITES can occur just in case the overlap between A and B is greater than 0, and the overlap between B and C is greater than 0, and A is not identical to C. And if you think about it, this is pretty intuitive, because in order for the subject to not be able to discriminate alpha from beta, presumably there's going to have to be some overlap between their experience of alpha and their experience of beta, and then same thing for beta and gamma. And then in order for the subject to be able to discriminate alpha from gamma, presumably there's going to be have to be some non-overlap between A and C, between the experience of alpha and gamma. So in other words, A and C presumably will have to be distinct from each other. Okay, so this is just a diagnosis of the conditions under which a phenomenal SORITES can occur. This is actually something that has been discussed before. Some people have thought that phenomenal SORITES cases occur in these sorts of situations. What I want to do is to go even further, because I think that with the regional framework, we can not only get a diagnosis of these kinds of situations, but we can also develop a probabilistic model of the phenomenal SORITES. Here's the hypothesis. It's very natural to think that the probability of a phenomenal SORITES occurring corresponds to the overlap structure of the relevant regions. So in other words, the chances of phenomenal SORITES will, let's say, go up when A and B overlap more, other things being equal, or B and C overlap more, other things being equal, and will go down when A and C overlap more, other things being equal. Okay, so this is a hypothesis. Here's how we actually develop that probabilistic model. What we first need to do is to develop a formal definition of the degree of overlap. There's a very natural way of defining that. We just take the size of the intersection over the average size of A and B. And with a definition of degree of overlap, we can define this probabilistic model, where the idea is that the chances of a phenomenal SORITES occurring between regions A, B, and C, which represent mental qualities that themselves represent stimuli, alpha, beta, and gamma, is equal to the degree of overlap between A and B times the degree of overlap between B and C times 1 minus the degree of overlap between A and C. Now, it'll probably take a moment to think about the structure of this model, but here are some nice formal features. One, we're always going to get an output between 0 and 1, and that's what we want out of a probabilistic model. Two, the greater the overlap between A and B, or between B and C, the greater the chance of a phenomenal SORITES occurring. That's something that I noted a moment ago that we want out of this model. It seems like if A and B overlap more in how they're representing their the stimuli that they're representing, then the subject should be more likely to judge that alpha and beta are the same. If either the overlap between A and B equals 0 or B and C equals 0, then the chance of a phenomenal soriety is equal to 0. That's just the limit case of the second desideratum. Also, if the overlap between A and C is greater, then the chance of a phenomenal soriety goes down. So in other words, if region A and C overlap with each other more, then the subject is less likely to judge that alpha and gamma are distinct from each other. And then finally, if the overlap between A and C is 1, then the chance of a phenomenal soriety goes down to 0. Now, one thing to note here is that this is all factoring out noise. Of course, things like psychophysical noise is going to complicate this. But I think that if we do factor out things like noise, then this provides a natural model of the phenomenal sorieties. So this is the second application. And I think this is a pretty cool application as well. I mean, there's a lot of philosophical literature on the phenomenal sorieties. Philosophers often wonder, should we characterize the phenomenal character of a subject's experiences in these sorts of cases? But this allows us to go further and formalize things and develop a precise probabilistic model of when these situations can occur. And to develop this model, what we need is the regional framework. Okay, last point that I want to cover is what I'll call the isomorphism thesis. That's the thesis that mental quality spaces are isomorphic to perceptible quality spaces. If you look in the relevant literature in philosophy and cognitive science, you'll see that this is very often just taken for granted. And I think if you think about it, it should strike you as very plausible, especially because if you actually look at the procedures that are used for constructing quality spaces, well, the procedure is that first we put subjects in psychophysics experiments and make them make a bunch of perceptual discriminations. And then we take that perceptual discrimination data and use that data to construct a perceptible quality space of, for example, colors. And then we extrapolate from that perceptible quality space to a mental quality space. So given this extrapolation step, it's very natural to think that mental quality spaces have to be isomorphic to perceptible quality spaces. But one consequence of what I've argued is that the isomorphism thesis is false. And the basic argument is simple. Mental qualities have precision structure, perceptible qualities don't have precision structure. So mental quality spaces aren't isomorphic to perceptible quality spaces. So therefore, the isomorphism thesis is false, contrary to what is standardly assumed. Now, if I had more time, I would develop a more refined version of this argument. I think that the real version of this argument requires appreciating the distinction between imprecision and indeterminacy that I briefly alluded to earlier. But I'm going to skip that argument just for purposes of time. We could talk about it in Q&A, or you can see the full argument in the paper if you want. To recap, what I've done now is I presented the regional framework. The core idea is to represent mental qualities via regions, where size of region inversely corresponds to degree of precision. I discussed the formal elements of the framework, and I've now talked about some applications and implications. I showed how the regional framework enables us to develop a formal measure of discriminatory grain, a probabilistic model of the phenomenal sorieties. I didn't talk about empirical investigation, but you can make some extrapolations and inferences from what I've said about the implications for empirical investigation. And then I've argued that the regional framework entails that the isomorphism thesis is false. The very last thing I want to say is to just take a step back again and to return to the big picture. So what I've presented today in this talk, as well as my whole research program here, is developing what I've recently been calling mathematical phenomenology, or the application of formal tools to the study of conscious experiences. And there's not a whole lot of work on mathematical phenomenology at present. The one thing I'm impressed by is the way that the organizers of this seminar have collated researchers across different disciplines. And I think that the formation of the Association for Mathematical Consciousness Science provides a nice opportunity to unite those of us that are interested in these topics into a community. But my own work is aiming to make advances in mathematical phenomenology, not only on how to model mental qualities, but also on other topics about the structures of conscious experiences as well. And I guess my own view is that if we really want to understand consciousness in a systematic way, then one of the most promising ways of doing that is going to be to examine its structure and to develop mathematical models of that structure. That, in my view, is what's going to be needed to move the field of consciousness research closer to a systematic science. Thank you.